single slit diffraction. Mathematical derivation. The experiment setup is as in this figure. The parallel beam shines through a single slit. The slit width is d. On the other side, we have viewing screen. The distance from the slit until screen is L, and L is much greater than D. The parallel beam can be obtained by point source plus a lens, or you just use a laser beam. The experiment is we will observe the fringes on the screen. On the viewing screen, we will have a center wide bright fringe. Then on the side we have many bright fringes, but the center one has wide bright fringe. The intensity at any angle theta is given by I theta equal to I0 times sine alpha divided by alpha square, and where alpha is defined as pi d times sine theta divided by lambda, and all this quantity is in radians. So if you use calculator, you must set up this quantity in radians, then you plug in this formula. And I0 is light intensity at theta equal to 0. So I0 is the light intensity at center. The objective is to find this formula. For that purpose, we will have a side view of the experiment setup. Here is the side view. We have slit, the width is d, and on the screen we have y. We set up a coordinate along this screen. At theta equals 0, this dashed line is optical axis. We locate this point at y equal to 0. At any point, we say it's y. For arbitrary point, it's y. And this angle is theta. On the slit, we also set up a coordinate. The coordinate, we call this x coordinate. So here we write down here's x. Now, this point, the bottom point, x equal to minus d divided by 2. On the top of the slit, x equal d divided by 2. The center point we define as x equals 0. The width is d. Now, we draw a line from the center of the slit to any point, the viewpoint. We draw a line. This line, the distance from this point to this point is r0. The length from here to here is r0. Now, and L is from the slit to the viewing screen. This distance is L. L is greater than the slit distance D. According to Huygens and Fresnel principle, we have here the total wave amplitude at point y on the screen is the superposition of waves that originate from an infinite number of infinitesimally small point sources in the slit. So this slit we treat as infinite number of light sources, and every light sources radiate light wave. So what we do is we divide the total width d into many intervals. Here we redraw this diagram. In the slit, the center point is x equal to 0. At any point x, we divide, because we divide the whole width d into many small widths. So at point x, we have little interval is dx, and we treat dx as a light source, and this light source will radiate waves and propagate to the y, the viewpoint y. Now, I can claim that this angle theta and also equal to the angle between this red line and horizontal line. So we draw here. I state this angle equal to this angle, theta. That means all these light rays are parallel as long as L equal L is much greater than D. Okay. If L is much greater than the width D, then all this light ray will be parallel. I prove as follows. So consider two points on this slit. One is on top, one is bottom. Now, this point is y, the viewpoint. Now, I claim that if this L is much greater than the width D, then theta 1 equal to theta 2. I prove in the following. Tangent theta 1 equal y1 divided by L. So y1 divided by this L. So y1 divided by L equal tangent theta 1. And y2 divided by L equal tangent theta 2. So tangent theta 2 equal to y2 divided by L. Therefore, tangent theta 2 minus tangent theta 1 equal y2 divided by L minus y1 divided by L. So equal y2 minus y1 divided by L. And y2 minus y1 equal to d. So divided by L. So y2 minus y1 equal this d. So this is d. Now, in the experiment, d is about 0.1 or 0.2 millimeters. L is about 1 meter, 2 meter, or 3 meters in the meter of order. So this d is in the millimeter order, or much smaller than millimeters, 0.1, 0.2. Therefore, d divided by L approaches to 0. Therefore, tangent theta 2 minus tangent theta 1 approaches 0. Therefore, theta 2 approaches to theta 1. Therefore, these two red lines are parallel as long as L is greater than D. So here is the proof. Here is the proof. The contribution d psi at point y to the total amplitude on the screen from the point at x equal to 0 is d psi y equal a times dx divided by r0 times cosine k r0 minus omega t. And k is wave number equal 2 pi divided by lambda, and lambda is the wavelength, and omega equal 2 pi f, and f is the frequency, and frequency equal 1 over period t, and a is the amplitude per unit width. So dy, this formula describes the wave originate at x0, and there's wave propagate to the point y. So let's visualize this formula. So cosine kr minus omega t equals cosine 2 pi divided by lambda times r minus 2 pi divided by period times t. So what we do is we plot this function harmonic wave at different time. For example, at t equal to 0, cosine kr minus omega times 0, so equal to cosine kr equal to cosine 2 pi divided by lambda times r. If we draw this function, we will have this picture. and as function of r. Now, you see, because cosine function is this, cosine function is this. Now, from this point to this point is the wavelength lambda, and also from here to here is wavelength, one wavelength. Now, if we draw another time, let's say the other time, at time equal half period, t divided by 2, I have a cosine kr minus omega t equal cosine kr minus 2 pi divided by t time. Now t equal half period. So then I get cosine kr minus pi, also equal to cosine 2 pi divided by lambda times r minus pi. Now, if I plot this function, I will have this curve. You see, the wave moving to the right. This A point and B point. So I have here's A prime and B prime. Now, if I plot another time, at time equal the period. Now, cosine kr minus omega t equal cosine kr minus t 2 pi divided by t and time t equal kr minus 2 pi, and this minus 2 pi equal to cosine kr. So equal to cosine 2 pi divided by lambda times r. So I have this waveform, and this waveform is the same at t equal to 0. So my wave will propagate from here to here. Here, A prime became A2 prime, and B prime is B double prime, B2 prime. So I can visualize this the wave propagate to the right, along this r direction. So here, then t equal to half t, capital T, this wave, and then it will propagate even further. Now, this to visualize we have here. Now, R0 at the bottom indicate the wave is spherical wave. Now, for off-axis points for which x is not equal to 0, the contribution is dy d percent y equal a dx divided by r0 minus delta times cosine k r minus delta minus omega times t. Let's see this term. So, for off-axis point for which x not equal to 0, the contribution is this. Here for arbitrary point, which is not x0 at arbitrary x, now I have the contribution equal to this formula. So what I need to change is for above. So I have k times r0. What I need to replace, I replace r0 to r0 minus delta. So from here, I replace r0 with r0 minus delta. I have here. So at any point, the distance from this point to the viewing point y equal r0 minus delta. So as I said, all these lines are parallel. Therefore, Therefore, if I draw a vertical line perpendicular to this red line, this is 19 degrees. Now, R0, the distance from R0, from x0 to the y equal to R0. Now, the distance from x to viewing point y equal R0 minus this piece of length. This piece of length. And this piece of length equal, I define as delta. Delta equals x times sine theta. So from here to here is x. From here to here is x. Because this coordinate x equal to 0. This here to x. Now this angle is theta. This angle theta, so therefore this angle also theta. So x times sine theta equal to delta. So the distance, the length from x to point y, to viewing point y equal to R0 minus delta. So therefore, I have this formula, d psi y equal to a times x dx divided by R0 minus delta times cosine k R0 minus delta minus omega t. Now, the total contribution, we need to add up all the contribution from x equal to minus d2 divided by 2 all the way down to d divided by 2. So as we said, we need to divide the whole width into infinite number of dx, the sub-intervals. So we need to integrate all these things. That is, the total amplitude equal d psi 1, d psi 2, plus d psi 3, plus all together. But in our case, it is continuous, so we use integral. So integral d psi y and equal to here, x equal minus d divided by 2 to x equal to d divided by 2. Now this is integrand a divided by R0 minus delta. Delta is function of x. Delta x equal to x times sine theta. So cosine k R0 minus delta minus omega t dx. So we need to do approximation. R0 minus delta x is equal to 1 over R0. This is the reason. R0 is the distance from x0 to point view y, to the y. And delta is around this range. Delta is x times sine theta. My x is around d. It's in the order of d, the width of the slit. X is around order of d. Now, therefore, R0 is much greater than delta. So, R0 is much greater than delta. Therefore, R0 minus delta is approximately equal to 1 over R0. If in this case is true, so this term, the bottom, is not function of x anymore. I take delta out. I ignore this delta, so I move a divided by R0 out. I take a divided by 0 out of in front of integral sign. Now I need only integral cosine k times R0 minus delta minus omega t dx. So if I substitute delta of x equal to x times sine theta, I will get next formula. So I will get a divided by r0 times times the integral of this whole term. Now we have noticed k r0 minus k delta minus omega t. I cannot ignore this term. Although delta is small, delta x small, but I cannot ignore this term. The reason is this: k equal to 2 pi divided by lambda. K is wave number, is 2 pi divided by lambda, and times this delta. If my delta change, my delta is small, if I change in the order of lambda or half lambda, and this change in the order will be half pi or 2 pi in this range. Therefore my cosine will change a lot. Okay. Delta is in the order of wavelength. If my delta change half wavelength or whole wavelength, so the whole term will change from in the order of pi or half pi in that range. Therefore, cosine will change a lot. Therefore, I cannot ignore this term. So I have to keep this term. When I keep this term, I have the following. So a divided by r0 and times integral cosine k r0 minus x minus k times x sine theta minus omega t. Now, I move this term in the front. Then I move this term behind, k r0 behind. So I move this term here. So I combine this term as a b, and this coefficient in front of x, I call this term as a. So this is a, this is b. Now, I used calculus formula. So cosine ax plus b dx equal to 1 over a sine ax plus b plus an integral constant. So this can be simply proved easily because sine, your derivative of x with respect to x is the cosine. Your sine derivative, you change the cosine. Then you have a is coefficient. Then you derivative further, you have a. So this a cancel out. So I have cosine this term. So this is easily proved by the calculus. Now I have this one cosine. Then I employ this mathematical integral. So I have. So this one equal to 1. This is my a. I put on here. This is my a. And then here sine ax plus b. So I have here so this is my b. This minus k sine theta is my a. This is my a. Minus k sine theta is my a. This is my a. So I just employ this mathematical formula. I have this equation. Now I have to plug in the integral limits. One is top, one is bottom. So I plug in here. So x, if I plug in x to d divided by 2, I have here Now x equal to minus d divided by 2, I plug in here. So minus cancel with this minus sign, so I have here. Now, next step, these things I need to simplify. This term, the last term, I need to simplify. By using sine minus theta equal to minus sine theta. This is the property of sine. Sine is odd function of each argument. Sine is odd function. Okay? Cosine is even function and sine is odd function. Now, this one I can change as this. So this minus sign I can get in. I change minus k sine d divided by 2, and I change minus sign. I make this as bracket. I change minus sign in front. Now, next step, I need to simplify. This equation. I have a trigonometry function trigonometry identity. Here is this theta 1. Here is theta 2. I define this quantity at theta 1 and this quantity at theta 2. Theta 1, theta 2. I use this mathematical function identity. Sine theta 1 plus theta 2 plus sine theta 1 minus theta 2 equal to 2 times sine theta 1 cosine theta 2. If you're not familiar with this identity, I can prove easily as this. So this is the sum of sine. So sine of 2 sum, the angle sum, equal sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2. And this term is this sine theta 1 cosine theta 2 minus cosine theta 1 sine theta 2. So this term is this one and this term is this one. So when on the left side I add up, so the last term will be cancelled. This one cancel with this one, so I get 2 times sine theta 1 cosine theta 2. So 2 times sine theta 1 cosine theta 2. So I can prove easily here. Now, therefore, this equation I can simplify as 2 times sine this quantity cosine this quantity. So this is theta 1 and this is theta 2. I just put it here. I simplify the sum of 2 sides as products, multiply together. So now, and remember sine is odd function. So this I have negative sign. I have here front a negative sign. So this cancel out with this sign. So minus I get positive. So I obtain the following. What I did is at here I multiply d and I divide by d, and k is k on here, sine theta is here, and r0 I remains here, and a is remains at here. So what I do, I want to make the same quantity as the argument of sine. So k sine theta d divided by 2 and k sine theta d divided by 2. So I have here this quantity is the same as this quantity, and time cosine this factor. what we observe by our eye is, the time averaged intensity. That means time average of psi square at y. So what we observe, the amplitude we need to take square, then we get the intensity. So we make time average equal to psi square at y and time average. We use angled bracket to indicate time average. To use this kind of bracket to indicate average is due to Dirac in his book in quantum mechanics. So in the previous page, we have here psi at y equal this quantity. Now we need to take square of this quantity. Then we take time average. So what we do here, we take square, then here square. Now we also take time average, because this factor has nothing to do with time, and this also has nothing to do with time, so I can take it out. So time average, only we average this term, cosine square term, because this term has time t. T is on here, and so any quantity time average is defined as integral from 0 to t and divided by the period. And this one, when you integral mathematically cosine square kr0 minus omega t, when you do mathematically in integral, you get 1/2. You get 1 divided by 2. So therefore, this term I have only 1/2. So I can have 1/2. I put on here. So a square, d square, r square, r0 square. So I have 2 here. So this I remains here. This term I remains here. Now I define this quantity, this factor as time as I0. The whole thing in the front is I0. Therefore, I have I at any angle equal I0 times sine alpha divided by alpha square. And alpha is defined as k sine theta d divided by 2, because my k equals 2 pi divided by lambda. K is wave number, 2 pi divided by lambda. So I have here 2 cancel out. So I have pi d sine theta divided by lambda. This is our original formula in the beginning. So alpha equal to this quantity, and the light intensity at arbitrary angle theta equal to I0 sine alpha divided by alpha and square. So it is this. And if you plot this function, sine alpha divided by alpha is called sinc function. Sinc function. If you plot this function, the square, you will get this distribution. This distribution.